so we have we will get to the last part of the course, and it's very similar to what we saw. There's a scheduling and there is the optimal control. So let me go into that. So this is the difference is the controller design, event triggering controller. Okay. So in the event trigger controller, if you remember, yesterday I kind of covered. In the event triggered controller, you have a kind of a switch, and that switch stays here, and it decides whether to transmit the state vector through the network or not. Okay, so that's the purpose of an event trigger, and in order to make that decision whether to transmit or not, you have a condition called event triggering condition. Okay. Now, why are we doing that controller approach? Because if you remember, in the previous case, there's a lot of state vector going through this particular network, right? Every periodic sampled interval, there is a state vector being transmitted. So as the state vector being transmitted, and you have many systems, there's a potential for congestion, right? There's a potential for congestion. So if I have a decision, remember I said in Chicago and other places you have a little signal as you enter the highway. Unless that signal is green, you really can't enter the highway. Okay? So that signal is what we need to design. Now by reducing the amount of traffic, you are able to even further reduce and maintain the performance, because if you have multiple systems communicating, you can actually have more people communicating because you're reducing amount of traffic. Got it? So that's basically what the difference is between event triggered and here. So let's take a linear system. You see this here, and here you have the triggering mechanism. There is a triggering mechanism here that decides when this state XLK can be transmitted through the network. When the XLK is being transmitted through the network. So if you have a linear system, and here is the control input, you see that the XLK is the state. It becomes XLK when the event is initiated. That's the condition. And then you use the previous state value when the event is not initiated. So that means that you're holding the past state value, and that value is being used in the controller. Remember, the controller actually sends that. So the event error, you define the event error is equal to 0 when the event is initiated. So I'm able to send, when the switch closes, then this value is being transmitted. So XLK minus XLK will become 0. When it's not being transmitted, the previous value and the current value, if you take the difference, that value keep increasing, because the system will run in open loop. Okay? So this difference, you see that this difference keep increasing. So as it increases, you have to have a condition, and you can see this is the condition. So you select if the error, this error is less than some value sigma L times some constant matrices times square root of norm of the square root of the state. So if this condition is violated, if the condition is violated, then immediately the switch will close and the state is being transmitted through the network. Otherwise, you are not transmitting it. So the benefit with that is you are not transmitting the state every sampling instant. You see? So that reduces the amount of transmission. You are sending it through the network. So the scheduling protocol has to work less, because each subsystem will have fewer number of states. The sampling interval get stretched. This is called performance-based sampling. It's also called performance-based sampling because you are not using the Shannon's sampling theorem. That is, you are sampling twice the bandwidth. Here you are sampling basically whether the system becomes unstable or not. Okay, and this is mathematically driven. These values QL, B, and this is K, the gain matrix, PI. So this is basically the event-based sampling. So you can see that the other method, another one that we developed also, it's also called adaptive model based. So if I don't have A, L, and BL, then you can have an estimator, adaptive estimator. You see that X hat, AL hat, BL hat. So you're estimating that AL hat and BL hat, and you can use that information to decide when to transmit. Okay, and that essentially makes it even better, and that reduces the number of transmissions even fewer. So if you know more about the system dynamics, you can transmit lot less because you can actually precisely decide when the system is going to become unstable. You see? And so that method is called model based, and you can see that you can write this AL and BL as theta. See, theta L is equal to AL and BL, and then you are using an estimator. You can solve it using adaptive control, and here is the update law. See that this is the update law, and that generates lot less number of samples, and you can show that the parameter estimation error and everything converges to 0 asymptotically. Okay, converges to 0 asymptotically as k tends to infinity. So this is something you can do, event triggered control. So now what we are doing is we want to do that. We want to use a event triggered approach as part of the distributed. Now what is the advantage? Guys, what is the advantage? What is the advantage? I just said. Huh? You will save the bandwidth because you are not transmitting the state vector to the controller more at every sampling instant. You see? You are not transmitting the state vector at every sampling instant. And the same way, you are not transmitting the control input vector to the actuator every sampling instant. So that basically saves the number of transmissions, and that saves the bandwidth in the network. Got it? Okay. So here you are using those states, the sample states, event triggered states instead of the sample states, and use the same follow. You use the same method, and you get this is your control input. Okay, and you use the same thing that we discussed, the Q-learning, since it's a linear system. But the only difference is you're using the samples event triggered states. Okay, so you estimate that, and you are able to compute the control gain, and this control gain is basically the event triggered control gain. So once you have done it, you use the Bellman error, the stuff that we have done. You're tuning the parameter update laws. So I will skip all that. So all that is the same. All that is the same idea because you are using the same approach. Okay, and so what you do is you basically use the event triggered approach. You construct the error, event triggered error. We call the zero order hold. Here is the closed loop dynamics. KK is optimal gain. AZK plus BZK. This is all the poles are on the left half of the S plane, and this system is driven by the event triggered error. So that event triggered error becomes 0 when you at the sampling event triggered sampling instant. So this system is asymptotically stable. Okay, so now you see that you construct the threshold, and the threshold is a function of AZK and BZK. Now If I don't know AZK and BZK, I cannot come up with the threshold. So here we found a way to construct the threshold even if you don't know AZK and BZK. Okay? So that threshold is dependent on the system dynamics. In the adaptive event triggered, you saw that I'm using an estimator. You see that I'm using an estimator. So that estimator, what is doing? It is estimating A hat and B hat, and that information is used to tune the parameter update law. Also, it's used to determine when to transmit the signal. Okay? So this event triggered is very popular, and it violates the Shannon sampling theorem, but it works. So you have a stability theorem. It shows that when you use a initial admissible control, U0, an adaptive estimator is used to estimate H. Then you exist alpha L and the closed loop state vector ZL. They are asymptotically stable in the mean, provided the controller and adaptive estimator parameters are basically used. So this sigma L, the threshold, is determined by L0. Look at that, BLM. BLM is the upper bound on the control coefficient matrix BZK. And K hat is the estimated control gain, which is basically using that Kalman gain, which is the estimated value of the Kalman gain. So this is how you're selecting or deciding when to transmit. And by doing this, you are able to reduce the amount of transmissions going through the network. Okay? So if you look at the cross-layer design now, so the network layer uses the data rate. The physical system generates information to the cyber layer. Cyber layer generates the control signal. You determine the cost function from the physical system or the reward. The reward is used in the network layer, and that information essentially used in the scheduling protocol, and then that information is sent to the physical layer. Okay? So here we are using event triggered controller. Any questions here? Is the same. But cyber layer is basically a separate layer you are designing because there are a lot of stuff that goes in there. The application layer, there are some other things you could do in the application layer. Okay? So if you talk to the computer science people, the application layer, they have a dedicated stuff in the application layer. Anything other than the stuff is basically a different layer. We call that as a cyber layer. Because in the cyber layer, you could have a triggering mechanism, when to trigger, when to basically transmit. Okay? So that is the triggering mechanism. Okay? So any other questions here? Any other questions? So the cyber layer, that's why it is like a cyber physical system, Okay? So here is the cross layer design. The cross layer design is the same, like we talked about it before. You see that you are looking at the traffic. Remember that we already covered the beta I times the total traffic. And you see there are beta I is the weighting factor, this RLK is the traffic average payload traffic, and there are M subsystems, so you take the total traffic, and beta L defines the weighting. The higher the value, the more important. You are trying to minimize that J of K. This includes that term there. Okay? That's why it's called cross-layer design. You are taking it from the traffic, which is from the link layer, the amount of traffic you. So if you are using event triggered, you will have smaller amount of traffic because you are not transmitting every sampling instant. That is the difference. So otherwise, the system, the approach is the same. You take the two cases when it's scheduled, when it's not scheduled. You take the difference, which is delta j. This is the difference between when you are scheduling, if you don't schedule it, and that you are converting into number of bits. So each subsystem will have so many bits to transmit. That information is used by the scheduling program to decide which one gets the priority. You understand that? So the more you have to transmit, then the back-off interval will be smaller. Therefore, you get the priority. Okay? So we use that information in the computing the back-off interval. So here you see the number of bits is used to decide when to transmit, when to not to transmit, and that information basically is used. You are maximizing that, the difference. Okay? So you're trying to maximize the number of bits you're transmitting or you need to transmit. And that information is used in the back-off interval calculation. You see that? And that delta j is used here. So if you have more to transmit, your back-off interval will be smaller. So you will be given higher priority. Okay? And that basically makes the decision that you will transmit. All right? So here is the actual algorithm, the algorithm 8.3. Okay, the 8.3 which is same. So what you are doing is you calculate for a given sampling interval, you calculate the back-off interval for all of them, for different subsystems, based on this equation. Then all the subsystems are contending for the communication source. You find the back-off interval for the subsystem which has the smallest back-off interval, right? You find the subsystem that has the smallest back-off interval, and that is used to transmit. You will be given and it transmits the data. After the transmission is over, then you update the utility function. Once you update it, you update the time, and then again you broadcast all the utilities, and again you go back to the next sampling interval. So this continues in the link layer. You see? So the link layer computes the schedule, the application layer computes the cost, reward, and then you use that information both to minimize in the application layer as well as to determine the back-off interval. Okay? So and then what you do is you have m pairs. You see those. So you have a back-off interval. This means that you are basically given the transmission. Your pair obtains a wireless channel to transmit. So it transmits and then it backs off. Okay? So then it waits for the next transmission because here the media is busy because this second pair is transmitting, so it cannot transmit at the same time. This is the same time. See that? Same time. So it has to back off. So this is how you have a schedule and only one of them will be transmitting. Okay, you see that? Only one will be transmitting. So that's basically a schedule. And BI stands for back-off interval. You see that means that the subsystem is waiting for the channel to be free. This means that particular subsystem is transmitting data. And what data it is? It's basically the state vector. And here is the performance theoretical proofs that shows that by doing this, you are able to maintain the maximum utility. That network is being utilized maximum, So that, in other words, it shows that the network is not idle. Because that's important. Remember I told you yesterday, you have a highway, you are controlling how many cars are entering the highway. Imagine if you don't do a good job, then no car will be going through the highway. The highway will be empty. But the goal is to maximize the number of cars to go through the highway without any delay. You see, that is the goal. The same idea here. Okay? So all the proof is basically to show that this distributed scheduling works great. Okay? And we also talked about the fairness. Remember, in essence, you have to compute everybody has a chance to transmit. So this is the equation for fairness, and we look at the example. So here is the example. So now let me ask you, is this a linear system or a non-linear system? Is it a linear system or a non-linear system? It's a linear system, okay? So here you see that there are 6 of them that we are taking. The periodic sampling interval is 0.15 seconds. There are 6 of them. 1, 2, 3, 4, 5, 6. Now look at that. Each system, subsystem has so many bits to transmit. Okay? So there are 6 of them. Each of them have to transmit. One of them is 10 bits. The second one is 8. Third one is 6. Fourth one is 7. Fifth one is 8. Sixth one is 4 bits. So it has to transmit. So the one with the highest. So now what we do is the number of bits are defined. Here is the sampling interval. And here is the Q. R is given. The state vector initial value. X2 0 initial value. X3 0 because all these initial values. And we have to design an event trigger condition. And we also have to design the scheduling scheme. We have to compare this with ERR, round robin method, and greedy scheduling. So the argument state is defined as like this, just like we did. Look at the basis. The basis vector. x1 square, x1, x1, 2, x1, x1, 3, x1, 2 square, x1, 5 square, all that. And here is the learning rate. We are using the 0 order hold. Okay. The 0 order hold with the threshold value of 0.9. Now here is the event trigger. Now look at that. So the error, regulation error, all the errors converge. Now look at this plot. Here you see those the dotted line, that's the threshold. That line is the threshold. Okay, you see that it becomes 0 and then the error increases, it hits the threshold and then again the transmit becomes 0. So you see that like this. So whenever it becomes 0, that means it transmitted. Now if you plot the time, on the sampling instance, you will see that the sampling instance keep increasing. You understand that? Initially, the number of sampling instance will be equal to periodic sampling instance. Why? I already explained that. Why? Initially, the number of event triggered sampling instance will be equal to periodic sampling instance. Why? It's an open loop, but why? Why do you need to transmit more often initially? That is the learning phase. Remember, you don't know AZL, BZL. So you are learning, so you have to transmit. You don't want to let it open loop because it becomes unstable. But once you learn the matrices AZK and BZK, then you don't have to transmit too long. So you can stretch that sampling interval a lot longer. That is the benefit. So when you are stretching the sampling interval, what is the benefit using event triggered? What is the benefit? What is the benefit? I also explained. What is the benefit? Huh? Less number of transmissions through the network. That is the main advantage of event triggered. So you are reducing even more transmissions through the network by using a event triggered controller over non-event triggered controller. You see? So that reduces the amount of transmission of state vector through the network. You understood that? And that's why you see that there are few sampling instances. So, but otherwise you can see that the cost function, if it's a greedy scheduling, it's keep increasing, whereas with the proposed distributed scheduling, it's very small. The red round robin takes longer total cost. And fairness, look at the fairness. The fairness with the greedy round robin is the highest, like we discussed, right? Everybody get a chance. But our approach is close to 95%. It's still not bad. Whereas look at the greedy scheduling, it decreases as more number of subsystems are willing to transmit. Okay, so fairness, our fairness is not bad because our system is able to maintain higher levels of fairness. So 1 means it's fair. Okay, so conclusions, the interaction between network and control plant is considered properly, and the adaptive optimal based model based event trigger design essentially yields satisfactory performance for multiple pairs of cyber physical systems. A novel cross layer design is still cross layer because you are using information from the link layer. We are trying to minimize it as part of the cost, and then we are taking the value function for each subsystem and you are sending it to the link layer, and that information is used to maximize and to compute the back-off interval. So that information sharing, we call that as cross-layer design, and that helps with both the network as well as the physical system. Okay, any questions, guys? Any questions? Yeah. You mean it misses? Mathematically we prove it that it can miss unless something is wrong in the mathematics. So you see that how do you derive the event trigger condition is through Lyapunov. You see what I'm saying? Through Lyapunov stability. So if you remember this is where you are defining the sigma Lk, and sigma Lk is a function of the system dynamics and the optimal gain. So this derivation, this form of event trigger condition is derived by using Lyapunov stability. So that's why we call that as a performance based. So if you have done the math correctly, you cannot miss it. Got it? Any other questions? So you see that I did multiple things. I started with optimal controller for uncertain dynamics. I explained what happens when you bring a network, right? Random delays and packet losses. Then we did a lot of those controller designs. Then we said, well, there are a lot more things you could do when you have a network. So we brought in the scheduling, because when you have wireless network, multiple subsystems where they are sharing the same network, and that causes problems, right? Remember that. So then we defined a scheduling and said cross-layer design. Then we went one step ahead and said, well, we found out that you don't have to send data transmissions or the state vector and the control input every sampling instant, periodic sampling, because that also increases the number of data going through the network. So we use the event triggered sampling, where you can stretch the sampling instance. This way you have more bandwidth for the network and more number of subsystems can coexist. And that's the benefit of the event trigger control. You're still doing cross-layer design. Okay, any questions, guys? Yeah. Yeah, it is a function of the state. Yeah. Yeah, that is the ball. Yeah, the error, the ball is basically that's the magnitude. If it is exceeding certain value, if this condition is violated, that means you are becoming unstable. You are becoming unstable. So basically what you are saying is you need to transmit immediately. See, this through the violation of an event trigger condition defined by that. So if this condition is satisfied, then you don't have to transmit. So you see that you're reducing the number of transmissions. You understand that by using the event triggered control. The sigma is a threshold. That is through proof, mathematical proof. We are not covering it because I think that will more mathematics Lyapunov proof. That is correct. So it's using the Lyapunov proof. So that sigma L has to satisfy, you see that equation that I gave you. So if this is a positive quantity. So if this is a threshold, now where is that threshold? Remember I showed you in the plots. You see that line, the dotted line? That is the threshold. So, and the threshold is keeping down, right? It's decreasing. You see that. So because that means it's decreasing, that means that you are able to stretch the sampling interval for a longer time. Okay. So that means you're not transmitting. You only transmit at the steady state after a very long time. You're not transmitting every periodic sampling instance. So that would keep the network free of bandwidth so that others can transmit. That's the benefit of that. So a lot of things you can do. Any other questions, guys? Any other questions? Any other questions? That is correct. I think so. It is a function of the state. So there are a lot of different ways people have defined the condition. I agree with you. There are a lot of different ways. Here we define in terms of B and the Kalman gain, K. It's right. If you look at it here, that threshold is a function of, look at that threshold. The threshold, sigma L, is a function of some constant, and BLM is the upper bound on the control coefficient matrix, BZK, and KL hat, K hat is the gain. So all these things play a role. And since the K hat is varying, the threshold is changing. So the drawback of this is you need to know what is the upper bound for B matrix. Remember that? You need that upper bound here to compute the bound, to compute the threshold. You see that? Any other questions, guys? Any other questions? Yeah. If you take what? If you take any event, okay. But first do you guys understand what is the purpose of event triggered control? Do you understand that? You see that how we went in the course. You started and said when you have a system and you have a network in between, because everybody likes it, controlling it through remote. If you have a system, you bring a wireless network or a wired network within the feedback loop, you have a lot of problems. And what is the problem? The A matrix, B matrix, or the nonlinear is a function of packet losses and delays and all that stuff. We understand that. And that can cause the system stable. Even though you have a stable controller, right? Let's understand that. Even though you have a stable controller, because of those packet losses and delays, we have seen, right, more examples. It blows up. And unfortunately, we don't know the information, the exact information about how much delay you're going to have, how much packet losses you're going to have. Why? Why? We won't have that information. And why is that? Huh? No, it's because that is a network where that values can change very rapidly. We treat it as a random variable. So you don't have prior information about it. Only you know the distribution. Okay? So you don't know that. So as a consequence, the dynamics become uncertain. And therefore, you are using the Q-learning, or neural network to design the controller, right? That's what we did. But then we also realized that we haven't really spent time on the network side of it. How do I reduce the random delay? How do I reduce the packet losses? See, that's what the next step is. So how do I do that? I'm doing it through scheduling. You see? I'm using through scheduling. Why? Because scheduling, what does the scheduling do? It basically decides who goes first. Right? So that requires a cross-layer design, because you have a reward by the physical system, you have a link layer where there is a scheduling method. So we need some information for both, and the way we did that is by using the back-off interval. You see? So we did that. Then we said, even then we have done it, but you are constantly transmitting, because every controller uses periodic sampling. And so whether you like it or not, you are trying to send at every sampling instant, you are sending the state vector and the control vector input, right? Remember that. So how do I even reduce it without causing the system stable? Then I have to go for event triggered control. So the event triggered control has another switch. You, based on the performance, you are deciding, do I need to transmit that, even that minimum data? When the system is operating at steady state, nothing is changing, you don't have to transmit for a long time. So as the fewer packets go through the network, the delays will be less, the packet losses will be a lot less. You understand you see that? Three things we are doing now. So I want you to think this carefully. Okay, yeah. Okay, so let's say that you're controlling a system through, let's say, like a microgrid. Think about it, power grid. Power grid, a very good example where they have a lot of, network among multiple plants, because each plant does it. Process control is another example. In a process control, if you go to any refineries, they have different sub-plants in a big plant. Each part of the plant does some chemical processing. Okay? But they're all connected through a cable, like a network. And so they exchange information. In a power systems, they call different regions. There are different generators in each region. Depending on the demand and supply, you turn some generator on and off and all that. So sometimes you have to get power from a different region. You share power. So a lot of times the subsystems have their own states, and that can be modeled as a network control systems. These examples are network control. So when you're doing it, imagine you have a subsystem in a power system. There will be states. In that region there will be 2 generators. In a different region you might have 4 generators. So you are controlling the generation also. There are states. And that information, if you are transmitting through the network, could have potential congestion. It depends on how many sub areas you have, and it all depends on the bandwidth of that network. So power systems uses wide area network. Refineries also use that. Automotive systems, if you look at commercial automotive systems, they have a CAN bus. Under the CAN bus you have diagnostic modules, engine, final drives. They're all sharing that CAN bus, and they all transmit their status information, any maintenance information. All that information goes through that bus. That information is shared and stored in a memory. So they all use the same bus, and there's a potential that can lead into congestion. But in the CAN bus, it uses that CSMA-CD protocol. Now it's called CSMA-CA. CD is collision detection. CA stands for collision avoidance. So you want to avoid the collision, because what happens is whenever there's a communication going on, another guy starts sending a signal, it collides, and then both of them will back off. They found out the performance was going down. So now what they did was they used what they call collision avoidance. So you try to avoid collision. This way at least the system that is transmitting, or the subsystem, continues to transmit. The other guy can listen and then he can back off. So CSMA/CA, carrier sense multiple access collision avoidance. You want to avoid it rather than you colliding it. Think about it. There are cars going. If you don't have a signal light, you go and then you collide with the cars that is going. So they want to prevent that to happen in the packets. Because when there is a collision, what will happen? They have to shut down the lane, or and then that increases the delay for everybody. So this is the main reason, even in the network protocol. So here are some examples like power grid, refineries. If you go to refineries in Bombay, they use a big bus. And people are monitoring in that centralized place, all that information comes to them. Yeah. So those are the examples. And a lot of people are now interested to control some stuff in the lab. You know, remember when there's a COVID time? So COVID time, what happened, the students we put it on the network. Students can still do the lab experiments through the network. And there's only one person in the lab. He's watching so that nothing blows up. So he's the only TAs in the lab. Everybody is doing the lab remotely. And they're using their laptop or something, and they're connecting to the campus network. From there, they're doing the experiments. Yeah. Here is another example. So when multiple people are accessing the campus network, there could be some congestion. You know what I mean? Oh yeah. COVID time was a lot of things we learned. So this is another example. Okay? Any other questions, guys? Yeah. You need to talk louder. I know some of you, because I want the other students to listen and see what you are asking. Yeah, go ahead. Right? No, there are not other triggering methods. Which one? Right. Time is basically those are different types of event triggering, you know. So like in some cases you have a periodic, right? You are doing a periodic way of triggering, and that's based on the time. So yeah, so event is basically what you are saying is it's a function of time, but not every sampling instant. Let's say sampling instant is 0.15 milliseconds or 1 millisecond. So initially you may be triggering 1 millisecond till you learn the dynamics. But once you reach the steady state, you will be triggering only once in every 15 milliseconds. So that means you are not transmitting so often, right? Look at that. So how do you design that? You have to design it using Lyapunov stability. Don't forget that. So the time-based triggering is using the time, but then the easiest thing to do in the time-based is periodic. So that's what we do normally right now. The sampling instance that most of us use is fixed, a fixed duration. Okay, and so you saw in most examples we had a fixed duration event triggered. Yeah. Whereas in event triggering, you don't fix it. That fix is there, but then you will be transmitting as a function of those fixed intervals. So you don't transmit every time, once in 5, you know, that's something based on that design. That's called event. Event means the threshold. And whenever that it hits the threshold, the error, then immediately you transmit. That we call that as an event. But what happens if you don't transmit? System will become unstable. That's what he was asking earlier. Okay? And what other questions? What other questions, guys? So this is the last lecture material in the book. Okay? So tomorrow I will ask you any questions. So I encourage you to go through the material, all the slides, because tomorrow is the last day before the assessment. So I encourage you to come up with a lot of questions. Tomorrow we'll try to show you some other videos, right? Whatever we have done, and I will expect you to ask me more questions. Okay, because I expect you to go through those slides, at least theory, run the code as it is, see if it's working. Even I'm not there, you can run the MATLAB code, and you can look at it even if I'm not here, right? But at least you understand the theory a little bit. This way, at least you can ask me questions tomorrow, and then you will take that assessment exam on Thursday. Okay? So any questions before I pass the, the speaker to mic to Professor Bera? Today afternoon we don't have any tutorial. Tomorrow is the last day of class, and then we have a tutorial tomorrow afternoon. Tomorrow afternoon we're going to look at these event trigger, whatever, in this last one. That would be your last tutorial. Okay? So there is a code, right? You should be getting the code. Run them, and you run it and see. Already it was shared? Not yet. Lecture is shared, but not the math. Yeah, okay. All right. Any other questions, guys? After that, you won't reach me, or you can't. I'm not here. Okay. Any other questions? But you understood what is the difference between time? Time is based on a function of time. So if the fixed sampling interval is what time triggered. And the event is basically you are deciding when you really need to trigger. That's based on a condition, a mathematical condition. And that is what we call as event triggered. And that even further reduces the traffic in the network. Got it? All right. Any other questions, guys? Any other questions? It's 20 minutes after 12. So what are you going to do in the afternoon? After lunch? You will review the slides, understand the material, try to run the MATLAB code, and come back tomorrow morning with questions. And I'll show you videos, the event trigger also, some examples. One video at least. This way at least you see that these were all implemented on hardware. So it's not like theory as such. Yeah. Okay. Any other questions? Do you have a question? No? Okay. Okay, all right. So I'm going to pass it to Professor Bera. He might have a few